After this quite long chapter on transaction management, but it's also important, of course, for databases, we will now have 3 chapters missing until the end of the course. First, we will look in the next slides on probabilistic databases, then on column stores and in-memory databases very briefly, and then also a rather brief introduction to MapReduce framework for big data processing in data centers. For probabilistic databases, I have selected some literature. First of all, a book by Dansucho and others, and most importantly also a VLDB paper from 2004 by Dalvi and Susho, Efficient Query Evaluation on Probabilistic Databases, which would give a good overview. And then I have here some slides referenced from other courses on this topic, where I take some examples from, and you can check these sources out for additional information. So first of all, why are we talking about probabilistic databases? And well, this can be very easily motivated. Have a look at this example. So there are 2 forms completed by different people. And if you're looking now at these forms where handwritten information was inserted, it is not fully clear what kind of information we see. So it's not fully certain. And this is where probabilistic databases come into play. First of all, here we see that this person named Smith first marked apparently married here, but then wasn't sure if he or she was married, and then somehow made this change to the form and then put a mark to single. Now, if a computer tool will analyze this form, there can be a bit uncertainty about what is now really marked. We can probably see that it was probably now in the end a single mark, but nevertheless, there's still like some things to consider. Then we see here we have 185, perhaps if you're German or if you're using the same, let's say, notation as in Germany we do, you would probably say this is like a 185. But if you're looking at this one here below, this would also be a 185. Perhaps if you're from US or more like used to the notation they do, or like the way they're writing numbers, often I see you writing them, having them writing this for 7 and this for 1. So this would mean this would be a 785, right? On the other hand, here, at least when I write a 7, it will be like this. So anyway, now in this form we see we have a 185 here, perhaps also in the above picture, but this could also be a 6 somehow, right? So it's not really clear what we see, what information, and particularly here for the marital status, we see there's no mark at all. So perhaps wasn't sure what to mark, or they forgot what to mark. But however, this should be filled, right? So we have to assume something. And this is like also what probabilistic databases do. They would assume that all of these answers somehow are there with a certain probability, even so like these marks are not done. So if you're searching, for instance, for someone whose name is Brown and has like a social security number of 185 and is married, there's a certain probability that this is like the person you're searching, right? And there's a certain probability associated with the result tuple of our query. And we will look after the introduction to probabilistic databases what kind of ways we have to compute these probabilities. So before we talk about probabilities, we first of all talk about incompleteness. So an incomplete database is a finite set of database instances. So here are the individual instances. Here this one is the incomplete database. And each of these instances, these WIs, is what we call a possible world. And if you consider the example from before, here in this illustration again, we see that we assume for Brown, who did not mark any marital status, we assume all 4 possibilities: single, divorce, and so on. So you see what's going on here? These databases, these instances, are pretty much the same, except for the cases of the information we do not have for granted. So here the instances are the same, but now here we have these different choices for marital status. And the name is also kind of intuitive, possible world, because these are all possible to exist, but they are also like mutually exclusive, so they cannot be true or cannot be present at the same time in our real world, right? And of course, the marital status was not the only parameter that we were uncertain about. We also were not sure about the numbers, how we read them. Was it like 186 or was it 185 and so on? So you see, of course, we have to consider this 185 and 186 together with the marital status for Brown, and also all combinations together with the uncertainty about any information that Smith put. So if you have then, for instance, like these forms given to 200 million people, and these forms contain 50 questions, and 1 out of 10,000 of these answers is uncertain, so there are 2 options, let's say, then you have 2 to the 10 to the 6 possible worlds, and this of course is a huge number. And not only this, that you have so many of these possible worlds, each world, which looks quite small here, it's one small table here, but in this example here, on one world is a table of 50 columns, corresponding to the 50 questions, and 200 million rows. So for every participant in this poll, 1 row with 50 columns. So this is like a combinatorial explosion, obviously, because of these missing values and the consideration of all combination possibilities to create these individual worlds. So it's much more complicated than in the simple example. You see already in the simple example we had only 2 people, Smith and Brown, and only a few questions compared to 50. But even there you see the dots indicating that these are not all of the possible worlds that we have written down on the slide. There are more. So now how do we come to probabilistic databases, starting from these uncertain databases or incomplete databases? Well, a probabilistic database is simply an incomplete database with a probability distribution for the individual world. So every world gets a probability assigned. For instance, if we now assume that these are the 6 worlds and they are complete, so there are no dots here in the bottom, as you can see, then we can model it like this, that the first world has the probability of 0.1. Here we also have a 0.1, 0.1, 0.1, 0.3 and 0.3. And it's not difficult to see that these are adding up to 1. So the sum over the probabilities of these worlds is 1. Some worlds are more likely than others. This is like also the one point we do here. And this will also, of course, be important later on for the computation of the probabilities for the result tuples. Because in the end we will be able, or we want to be able, to write SQL queries, right? Select from our questionnaire table where name is Brown and marital status is married, for instance. And then there will be results, and the results will have a probability. Instead of writing these possible worlds in such a long way, in a wasteful representation, you can also think about a more compact representation, for instance, the so-called OR set representation, which is also very intuitive. Here, you're writing these certain information where you have only one possible choice, and then in these OR sets, in these sets of values, with an OR semantic, you would summarize all possible choices of these values. For instance, we have here Smith could have a social security number of 185 or 785, could have a single status or married status, and here we have Brown with like 2 choices in a social security number and 4 choices for the marital status because he or she did not mark anything. And now from that, of course, we can also derive possible worlds. Important is that we have here in this example no probabilities associated with the individual numbers here or different choices, because if you're looking at this form again, and you might be pretty sure that this is like a 185, and then the system who would do this character detection would come up with probabilities. For instance, we can say 185 is quite likely, it's 0.8, and this one has only 0.2, and here we have 0.25, 0.25, so 1 over 4, right, for each of these. And that means that in the end, based on these probabilities, we can compute also the probabilities for these possible worlds if you want to write it in the way we did in the previous example. So here's another illustrative example for probabilistic databases. Here we talk about people watching birds. So we have Mary, Susan, and Paul sitting in their home, in the balcony, let's say, in front of their house, and they're watching birds. And Mary is seeing a bird that we call here bird 1. Susan sees another bird, bird 2, and Paul another bird, bird 3. We assume that these are different. Let's say they're living in different cities. However, none of them is really certain about the species of the bird Mary, Susan, or Paul was seeing. So here we have Mary indicating that she saw a finch, and she gives a probability of 80% that this was indeed a finch, and she specifies 0.2 for the probability of seeing a toucan. Of course, they look really different. Perhaps she has no clue about birds, but anyway, that's an example. Susan says that the bird she was seeing is a nightingale with 0.65 or a toucan with 0.35. And Paul believes that it was a kookaburra with 0.55 or a toucan with 0.45. And based on these uncertain information, basically here we have two choices, here we have two choices, and here we have two choices. So we have 2 to the 3 possible worlds because we look at all combinations. For instance, Mary has seen a finch in the same table where Susan has seen a nightingale and Paul has seen a kookaburra. So finch, nightingale, kookaburra, finch, nightingale, kookaburra in this leftmost possible world here. And here we see a probability attached to this possible world of 0.286. How do we come to this? Well, it's simply 0.8 times 0.65 times 0.55. This should be 0.286. And we can do the same for all of these possible worlds, for all 8 possible worlds. And these are all the situations that could have happened if you assume that it was always one or the other and there's no choice that these are both wrong decisions, right? So just assume 2 choices each. Here you see an alternate representation from the previous information about the census data. We have one relation which is storing the social security number information, one relation storing the name, and one relation storing the marital status. This is called block-independent disjoint relations, BID. And if you're looking carefully what we do here, first of all, we decompose the information in 3 different relations. And of course, we have to be able to recombine them, these tuples. So hence we need a key that we call RID here. And this RID here for this first form that carried information about Smith, we use here T1 as the key. And here as well, it's the same form we're talking about. So these are alternate choices, right? So we either read a 185 or 785 for Smith together with these probabilities. Here we have only one choice because it's clear it was Smith. And here, for this form, we have 2 choices about being married or single with 0.9 and 0.1 respectively. So now we have, of course, the second form as well with Brown, which is denoted here by this T2 key. So we can also join that with 1 choice here and 4 choices here because Brown did not mark anything about marital status. However, important is that these blocks here, so the block with T1 and the block with T2 keys, are independent. So we can, in principle, have, or we will have, a possible world where we have 185 as the social security number for Smith, and 185 also with the social security number of Brown, which of course, if you're talking about social security numbers, should not happen because the same number cannot be given to two different people, or it should not be given to two different people. However, these blocks are independent. So how do we now combine these probabilities? Well, when we are joining, let's say, this tuple here with this one, it's the only choice we have, right? And then let's say we take the first one here, then the result tuple, which is like the join of these three, has a probability of 0.63, which is simply 0.7 times 1 times 0.9. And this means that in any possible world where this tuple here, so this together concatenated with this and this, how a join works, right, you know. In any possible world where this one appears, it has a probability of 0.63. The simpler way to write down probabilistic databases is so-called tuple-independent database, where we have only the tuples, so there are no blocks like in the previous case, only tuples, and every tuple has a probability. Here we have again tuple 1 with this probability 0.7, so there are no alternate ways the tuple could carry a social security number. It's only one in this situation. Of course, this is not the same modeling as on the previous example. There's only one example of a tuple-independent database. These tuples are all assumed independent from each other. Of course, we can join them based on the key. And then we have also, for this tuple, in a possible world where this appears, a certain probability of 0.7 times 0.9 times, well, 1, right? In a relation having n tuples, where every tuple having a probability of smaller than 1, so there is an uncertainty, so it has to be strictly smaller than 1, then we have 2 to the n possible worlds. Every tuple can be in the world or not. And the probability that it is in the world is given by the product of the corresponding probabilities. In this example here, we have 2 to the 4 possible worlds. The block-independent databases from before, from 2 slides earlier, they are also not really expressive enough for all cases because there could be dependencies between the blocks. We will not really go into detail because we will only look later on at tuple-independent databases to keep the discussion simple. So why would you need, however, dependencies between blocks? Well, if you're looking at this example with a social security number, we have a 185 here and a 185 here. However, we know from our experience from administrative tasks in whatever countries' administrations that in the social security numbers, there cannot be 2 people with the same number. So it cannot happen that this tuple is in our possible world and this tuple is also in our possible world. They are exclusive, mutually exclusive. So how this can be modeled is the following way. We assume we have some variables here. X is 1. Then this would be 185. And here for this 185, we assume, or we demand that X is not 1. So it's like a mutually exclusive way now. This 185 cannot be there in the possible world twice. Right? So we could have something like this. It's important to note that this is not the same in terms of the probabilities that we have seen in the previous example. There's just one way this database could be modeled using probabilistic conditional databases, PC databases. So having these variables x and y, and then having x and y also associated with probabilities for the corresponding values these variables can take. And depending on these variables x and y and the value they take on, these tuples are in whenever this equation here is satisfied. So if you're looking at all possible worlds, then the tuple is in, depending on if these x and y make these equations true. It is not difficult to see that tuple-independent and block-independent disjoint databases are special cases of these databases where you have these equations. For instance, you can model these tuple-independent databases that we have seen before. This looked like this. You can also model it like this, where you have these equations and you give these equations certain probability, right? These variables. In this case, it's only one variable here. So that's the same, obviously the same modeling that you can do here. So what does all this mean for the semantics of the query evaluation? That means if you have a query queue in the probabilistic database, what is now the result? Well, if you have a database, a certain database with possible worlds, then the result of the query in the so-called possible world semantic is simply a set of query answers, which is apply the query on world 1, apply the query on world 2, and until you apply the query on world n. That's not really that what you want to have in the end, because you would like to see tuples associated with probabilities, but this is like at least a start to this problem. What does it mean to execute queries on uncertain databases? Here you have the possible world semantic. For these queries and incomplete databases, which are enough in this case because we first of all do not talk about probabilities, we can look at answers, and we can call answers certain if they exist in all possible worlds within that incomplete database. And we can call an answer possible if there exists at least one possible world in our incomplete databases where this tuple t is in the query for a specific world. Yeah, for one is enough. So here we have, in this example, we have 6 possible worlds which are depicted on the left-hand side. And let's look at this query. So this database here is called census because of the census information stored in this database. The schema is social security number, name, and marital status. And if we have a query like this, so we do an existential quantification over n and m, that means we want to know the social security numbers. That means we have 185 as a certain answer, and possible answers are 185 and 186. Why is 185 a certain answer? Well, because no matter which world we look at, this one or this one or this one and so on, 185 is always included in these worlds. However, 186 is an answer in some of these worlds, but not in all, because for instance in this world here 185 is not included as a social security number. In a different query here, we have again the same table, obviously, and we're looking for n, that means a name. And then we see that Smith and Brown are both certain and possible answers, because no matter which table you're looking at, so which world you're looking at, Smith and Brown are always in the result. Now let's go for probabilistic databases, which are again incomplete databases just having also this probability distribution. We're looking now at the probability of an answer tuple, which is simply then the summation over the probabilities of these worlds where the tuple is included. So the probability of a tuple is looking at the set of all probability values of these worlds such that T is in the result if you're executing Q on W1 world, WI world, sorry. So now we take the same probabilities from some slides ago, and if you're doing the same queries as before on the slide, we're getting, this was obvious because 185 is a certain answer, we're getting the probability 1. Here we're getting the probability 0.6 for 186, social security number, and for the names, of course, we get for Smith and Brown the probability 1, because they appear in all of these worlds as query results, and the sum of these values here has to be 1, as we have seen earlier.